Hi everyone, my name is Jinghua Piao from Tsinghua University. It is a great pleasure to be part of this workshop on social simulation, and I really appreciate the invitation to join you all. However, unfortunately, due to the visa issues, I wasn't able to make it to the venue in person, so I'm joining remotely today. I'm very happy to share some of our recent work on exploring large language model agents for piloting social experiments under the project we call AgentSociety. Let's begin by recognizing a simple fact. Human behavior and social systems are incredibly complex. People's actions are influenced by emotions, culture, incentives, and social norms, all interacting at different scales. This complexity makes society very hard to predict and even harder to simulate or intervene in effectively. Yet, over the past 150 years, social scientists and natural scientists alike have tried to make sense of this complexity through models, theories, and increasingly through computational approaches. So the question is, how do we actually study such a complex systems like human society? One traditional approach is to run social experiments. These are very powerful tools for testing hypotheses about human behavior and social systems. But in practice, they face major limitations. They are very expensive, slow, and often raise ethical concerns. For example, the Stanford prison experiment had serious psychological consequences, and large-scale policies such as the universal basic income policies are very difficult to test in real life due to financial and political constraints. Moreover, as AI and automation reshape the workforce, the need to understand social responses has become very important, but also very difficult to explore through real-world experiments alone. So we face a dilemma. We need better tools to explore society's behavior, but the traditional methods often fall short. So we need a new tools. Think of it as a test bed for social experiments. Just like engineers use wind tunnels to test aircrafts, we can use simulated societies to test policies, ideas, or interventions without the risk and cost of real-world trials. A good testbed has three key qualities. First, it should be realistic enough to reflect essential social dynamics. Second, it should be safe and low cost, allowing for rapid iterations. And third, it should support imaginative exploration, letting us to ask what if and explore counterfactuals. With advances in computing, we can now start building such environments, not only for predictions, but also for understanding. As Feynman once said, what I cannot create, I do not understand. In this spirit, we approach social science from a generative perspective, by building models of society from the bottom up. One example is Earth 2.0, a first principles simulation where the NVIDIA tried to reconstruct the physical world based on basic rules. A question is whether we can do the same for the social systems. In natural science, we often break down complex systems into very basic elements, like atoms or molecules, and then rebuild them to understand larger patterns. In social science, we can take a very similar approach. Instead of molecules, our building blocks are individuals. From these micro-level agents, we can try to reconstruct the dynamics of larger human groups, organizations, and societies. This is where agent-based modeling comes in. It is a method that allows us to simulate collective behavior by defining how individuals behave and interact, and then observing what emerges at the macro level. So, just like physics or biology, we now can study society by building it from the ground up. There are many different types of agent-based models. There are three very important categories. The first one is rule-based models, such as the very famous Sugarscape. And the second one is equation-based model, like the social force model. And more recently, machine learning-based models such as the AI economist comes out. Overall, this model tries to generate realistic social outcomes from the very basic assumptions about agent behavior. But here is a limitation. They often rely on fixed rules or equations that do not reflect how real people think or speak. In real life, we always use natural language, and that's where large language model comes in. Large language models like GPT and DeepSeek have shown remarkable reasoning, role-playing, and problem-solving abilities. First of all, large language models are strong at reasoning. They can solve complex tasks, generate creative ideas, and even outperform humans in some domains. And beyond reasoning, large language models can also mimic human daily life. They can simulate social interactions, reproduce echo chambers, and predict the outcomes of real social experiments with high accuracy. Moreover, they are becoming embodied. They can understand multimodal information, infer humans' mental status, and perform human-like tasks through robots. These are not just linguistic systems. They can act and perceive like our human beings. To explore the potential of large language models to pilot social experiments, we first made some very brief attempts. The first exploration is about polarization. We are wondering whether these large language model agents can simulate polarization, one of the most important emergent phenomena in modern societies. And moreover, how do the agents' opinions evolve, and what mechanisms drive them? To study this, we built large language model agents with only the most basic social capabilities. No any predefined rules, no hard-coded behaviors. Everything these agents do, including how they talk, form opinions, or respond to others, comes entirely from the language model itself. This allows us to observe how complex groups' behaviors can emerge purely from language-based interactions. What we found is very striking. These large language model agents spontaneously develop polarized opinions through long-term interactions. And agents with very similar opinions cluster together, reinforcing each other's beliefs, forming these echo chambers, just like what we observed in the real world. And moreover, all of these phenomenon, polarization, and these echo chambers emerge purely from these interactions among these agents. We do not impose any predefined instructions. This is not a coincidence. It reflects a deeper alignment between how humans and large language model agents behave. At the microscopic level, we see agents making decisions following social mechanisms, like the selective exposure and the confirmation bias. at the interactions levels, echo chambers and backfire effects emerge. And at the system level, we observe clear polarization patterns, just like in the real societies. Importantly, none of this was built in. It all grew out of the model in its own language and the interactions capabilities. Next, we turn to a very different domain, macroeconomics. We wonder whether large language model agents can also make realistic economic decisions. To explore this, we develop Econ Agent, a framework that uses large language model agents to simulate human-like behavior in macroeconomic environments, such like spending, saving, working, or reacting to policy. This allows us to build more adaptive and behaviorally rich economic simulations. Through extensive experiments, Econ Agent produced more stable and realistic macroeconomic indicators, like the inflation, unemployment, and GDP. Compared to the rule-based agents, large language model agents generate results that better match empirical patterns. They also reproduce well-known macroeconomic theories, such as the Phillips curve and Occam's law, directly from their interactions and decisions. Based on these previous explorations, we built AgentSociety, a simulation platform empowered by large language model agents. AgentSociety can serve as a foundation for studying complex social systems by combining language, interactions, and environmental contexts. This platform helps us to scale up from the individual agents to larger populations and social dynamics. Each large language model agent in AgentSociety has three main components. The first is the profile and status. This includes demographic information, personality, economic background, and social relationships. It forms the foundation of who the agent is in the simulated society. The second is mental process. Agents process emotion, evaluate needs like safety or belonging, and make sense of their surroundings through cognition. Finally, we have social behavior. They are not random. These social behavior are driven by agents' internal mental process. For example, an agent feeling unsafe may avoid crowds, while one with strong social needs may seek out conversations or group activities. This behavior includes mobilities, social interactions, employment, consumptions, and other daily activities. All these behaviors unfold in a dynamic environment. The agent's memory, both objective events and subjective experiences, feeds back into the whole system, allowing their continuous adaptation. These agents do not exist in isolation. They live in a realistic societal environment. In the urban space, agents walk, drive, or take public transportation across a mapped city. In the social space, they interact through conversation, form social networks, and exchange messages, both online and offline. In the economic space, they work, earn money, consume, pay tax, and contribute the indicators such as the GDP. All these three spaces allow these agents to live social life grounded in realistic environments. Moreover, modeling complex social dynamics requires scale. Many phenomena like polarization, inequality, or contagions only emerge when large numbers of agents interact over time. To support this, AgentSociety runs on a powerful simulation engine that allows thousands of agents to act interact, and evolve in parallel. This makes it possible to study not just individual behavior, but full-scale societal patterns. Here we show a snapshot of simulated social life at two levels. On the left, we follow one agent's full day. This person has very limited income, so he spends 8 hours working, eats simple meals, and have limited time for leisure or socializing. His choice reflects personal constraints, just like those observed in the real world. On the right, we zoom out to see how hundreds of agents live together in the same city. We observe patterns in mobility, work, interactions, and how different lifestyles emerge across neighborhoods. This illustrates how AgentSociety platform supports both the fine-grained individual behavior and the large-scale social dynamics in a shared environment. With this AgentSociety platform in place, we can now design and run some social experiments, just like in the real-world research, but inside a controlled, simulated society. We explore a wide range of scenarios, from the political polarization to economic policy like universal basic income, to information spread and even natural disasters. Each experiment helps us to test theories, evaluate interventions, and better understand how society responds to changes. Our first experiment explores polarization, how social groups divide and reinforce their own opinions. Here we create three groups. One control group with free interactions, a homophilic group where agents mostly interact with like-minded peers, and a heterogeneous group with more diverse social exposure. We observe strong echo chamber effects in the homophilic groups. After the simulation, we surveyed these agents to evaluate their emotional responses to out-group members. Interestingly, we find that cross-group contact can help alleviate affective polarization. Our second experiment looks at the effects of universal basic income policy. We simulate two groups, one with UBI and the other without, and compare their behaviors and mental status. We find that universal basic income policy reduces depressions, increases consumptions, and generally improves human well-being. These observations mirror findings from real-world universal basic income experiments. We also conduct open-ended interviews with these agents, asking why they support or oppose universal basic income policy. Using grounded theory to analyze their responses, we find that their reasons, such as the fairness, incentives, or economic security, are strikingly similar to what we hear in the real human interviews. Our third experiment studies the spread of inflammatory messages, a major concern in online platforms today. We simulate four groups, one control group with no harmful content, a group exposed to inflammatory messages, a group with node-level mitigation strategies, such as the account suspensions, and a group with path-level mitigation strategy, like the content removal. We observe that how different strategies affect messages diffusion, user engagement, and emotional reactions. This allows us to evaluate not just how toxic information spreads, but also which interventions are more effective. Our fourth experiment simulates the impact of a hurricane on human mobility and behavior. We divide the simulation into three phases: before the hurricane hits, during landfall, and after it passes. We observe how agents respond through evacuation, shelter seeking, and return to normal life. When we compare the simulated mobility patterns with real-world data from SafeGraph, we found a strong match, achieving 87% accuracy in reproducing the disruption and recovery pattern. This shows that large-scale agent simulations can also capture realistic responses to external shocks. This visualization shows how mobility patterns shift across time. Before the hurricane, most agents follow routine daily movements. During landfall, activity drops sharply, especially in high-risk areas. And after the storm passes, mobility gradually recovers. To make simulation design more accessible, we developed AgentSociety 1.5, a visual platform for building agents and experiments. Users can create, modify, and observe simulations without writing code, making the platform useful for both researchers and policymakers. In AgentSociety 1.5, we break down the process of designing a social experiment into 4 key components. The first is large language models. You can choose the type of language models that empowers the agent's reasonings and communication. Second is the map. You can select the environment where these agents can live, including the urban layouts, landmarks, and public spaces. The third is the design of agents. You can configure the population, including their demographics, personality types, and social profiles. Finally is the workflow. You can design the structure of the environment, including the policy, interactions, and the data collections. We warmly invite you to try out our platform, AgentSociety, and experience how large language model agents can be used for social simulation. Here is a short video about how you can use our platform for your social experiments. First of all, you can define the underlying large language models for your agents, and then you can set up some other parameters for your experiments. Then you can define your map, and here is where these agents live. And then it comes to the most important parts for your social experiments. It is the agent configurations. You can define its demographics and design its prompts, and also can use other parameters to control its behaviors. Moreover, we also provide some templates on our platform. And then it comes to the workflow configurations. It defines how you can run your experiments. In our platform, you can use a timeline forms to organize your experiments. You can use different data collection methods. And finally, use your defined large language model agents, map, agent configurations, and the workflow design. You can run your experiments. Please feel free to try out our platform. Thank you so much for listening. We are really excited about how large language model agents can open up new ways to do social simulation and social experiments. If you are interested in our project, you are very welcome to try out our platform, AgentSociety, and see what you can build or discover with it. And of course, feel free to follow our work, and we would like to connect and collaborate with more of you in the community. Thank you.